Good afternoon. This is your lecture 8, Analog Microelectronic Circuits. And in today's class, we will continue a discussion on the current voltage characteristics of MOSFET uh, by deriving the current equation. So in the previous class, uh, we have done certain things in previous class. We understood the channel formation, right? This is your sixth lecture. We understood the structure, we understood the channel formation, then we spoke about threshold voltage, then we have looked how the current and voltage are related from the operation. By understanding the operation, we have just plotted this, and then we understood the tapering of the channel as you increase your VDS voltage. And finally we also saw that as you keep on increasing your VDS voltage, and when it crosses a particular voltage called VGS minus VT, it will actually go to saturation, or the current will be sustained. That was made clear in the last lecture. Yeah, eventually in this. So a depletion region will be formed, and across that high resistive depletion region, the electric field, the voltage will be dropped, and that electric field will be attracting or sweeping, drifting the electrons which is reaching to the this end, to the drain end of the channel. Even though the channel is pinched off, the current will not reduce to zero. Current will be maintained through the electric field because of the application of VDS. Yeah, that we understood. And further, from that understanding, we divided the different regions of operation as cutoff, linear, and saturation region. We have written the voltage conditions for all the three regions, and directly wrote the current equation, like assuming that you have seen this equation in even semester 1, right? So that is what we have done. And we also looked at the units of process transconductance parameter, or those things. And we have also seen that W by L is called as aspect ratio. Now with the current equation, that too in saturation, we proceeded in taking one sample equation of giving mu and Cox is equal mu and Cox Vt and W by L value. With that, we have also drawn the drain characteristics or output care of the MOSFET. Now from that drain and output characteristics, we have also drawn the transfer cara and understood that the VGS minus VT, or the saturation voltage, it is actually varying, or as you keep on increasing your VGS, you will actually get a higher current, and also your uh, pinch of point or the pinch of voltage is actually getting shifted towards the right. That is also clear from this discussion. So today we will continue current voltage characteristics. So what we will do is we will try to arrive at, we will see both graphically and analytically the current voltage relation, the relationship between current and voltage, right? So this is your lecture 8. So put a message in chat box in between if you are not following. Definitely I'll open for discussion after completing this current voltage characteristics. Right. So far we understood that when you apply a VGS, yeah. So when you apply a VGS, application of this VGS will definitely induce a channel. Right. So giving VGS will induce a channel. That too, we have to make sure that VGS is greater than VT for the channel to be present. Now with that channel, when the channel is present, if you're applying a drain voltage now when this channel is present, when we apply VDS, what we can expect, since channel is there, when we apply VDS, drain current will definitely flow. Now that drain current I will always denote using the notation ID. Now our intention here is actually to calculate or to arrive at an equation for this ID. So the objective here is actually to arrive at equation for ID. Now, when I arrive at an equation, I should consider all the cases. Initially, when there is no VDS or when your VGS is less than VT, your current is 0. And then we have identified two regions. One is linear region and another one is saturation region, right? So our objective is actually to arrive at an equation for ID. So let me start like this. When VDS is very small, since I am looking for drain current, I am considering that there is a sufficient VGS is given. Now we will not talk about VGS. VGS is already there, which is more than VT. Now when VDS is very small or when a small VDS is applied, what is happening? Let me look at the channel. This we have discussed already, but still we will look at that again. This is the source end and this is the drain end. Now VGS is the voltage which is applied here. This is plus minus VGS. Right. This is your oxide or whatever it is, and you have source and drain at both ends, and this is nothing but your channel. Now when you have a VGS, the channel is present, so assume that this is your channel. Now when your VDS is small, that means you have actually applied a VDS also here. And when this VDS is small, I can consider that the net voltage or the voltage between the gate and various points. Now I am looking at actually I wanted to know how much charge is there in the channel. Now that depends on the voltage which is available in the channel. Now initially when your VDS is 0 or when your VDS is very small, the voltage between the gate point, this point, and various points in the channel. So assume that these are the various points. Now throughout these points and the voltage between all these points with respect to gate. So at source end I can write it as VGS itself. Now from here till this point, if your VDS is 0, here I can write this as VGD. Right. Now so at this end, at source end, the voltage is VGS, and at drain end the voltage between gate and that point is VGD. And in between you can find there are so many points between source and drain, and even the voltage difference between those points with respect to gate will be equal to VGS when your VDS is very small. I hope that is clear. Right. Now your VGS is equal to VGD when VDS is 0. Now I am considering one more case. I know that Vs is 0. Now your Vd, if it is few millivolt, very few millivolt, say very low value of millivolt, then also I can consider, under this condition also I can consider that since your drain is very small, if I assume that approximately equal to 0, then also I can say that Vgs is equal to Vgd. So why I am making this point is I am trying to say that when your VDS is very small, the voltage between gate and various points along the channel remains constant. That is the point what I'm trying to make it over here. I'll just write it here. When your VDS is small, the point what I'm making is the voltage between. What I'm going to discuss now is what you already know. We are expressing using some expressions like analytical expressions, and also we are looking the same thing in a graphical way. So what I'm making here is voltage between gate and various points along the channel that remains constant, or I can say that is approximately equal to voltage at source end itself. Right. I hope this is clear. Right. Now in that case I will say that the effective voltage between gate and points in the channel. So look at this. So this is source and this is drain end. Right. Now I'm applying a voltage I'm applying a voltage VGS. I'm just pictorially representing. I'm applying a voltage VGS. Now VGS has to be what I can say is VGS has to be more than VT. Say for example, this is the VT. Now when I apply VGS, VGS has to be equal to or slightly more than VT. Then only I will actually get a channel, right? So I will mark this as VGS minus VT, the total voltage being VGS, right? So I will write a point here. The effective voltage between gate and points in the channel. So for a channel to form, your VGS should cross VT. With that understanding, I am keeping my VGS greater than VT. Now, till VT there is no channel, but when it is just VT or when it is more than VT, a channel is present. So I am writing this statement: effective voltage between gate and points in the channel is equal to, what is the effective voltage in the channel now? I have to apply VGS, which should be more than VT. Right. Now, what is the effective voltage? Can I get answers in the chat box? What will be the effective voltage between gate and the points in the channel, or between gate and channel now? Can I? Yes, it is VGS minus VT. That is the effective voltage. So, for those who are wondering what is this VGS minus VT, it is actually we are applying a voltage which is more than VT. So, the effective voltage that is creating channel is nothing but the difference, the excess voltage what I am applying there, which is VGS minus VT, right? So, this voltage is otherwise called as excess gate voltage, or we call this as overdrive voltage. Right. So the effective voltage between gate and points in the channel is nothing but VGS minus VT. Now, if this is the voltage, definitely this voltage will attract some charges. Right. Now I will write. So this voltage attracts charges, and the channel charges can be expressed mathematically. How will I express channel charges? Channel charges can be expressed as charges can be written as Q. Now I'm just writing the magnitude. I know that what I'm considering here are electrons. I'm just writing the magnitude. Now I know the basic equation, Q is equal to CV. So your charges will be proportional to the applied voltage, the effective voltage in this case. Now I can write Q is equal to, or Q is proportional to, the effective voltage here is VGS minus VT. That is the effective voltage, right? Now that is proportional to VGS minus VT, or that this proportionality can be, in fact, I can take out this proportionality if I find the capacitance there, right? So this should be equal to VGS minus VT. Then I should actually write the capacitance here. Now what is the capacitance? In the previous class, one more thing we discussed, the capacitance of this MOSFET. Yeah, where did we do that? Yeah, here. We have the oxide capacitance is not, we are not expressing that in farad, but rather it is expressed in farads per meter square. That means this oxide capacitance is nothing but a unit area capacitance. This is unit area capacitance. I forgot to mention that day. So this is unit area capacitance. Now if I want to write the total charges, I should know what is the total capacitance. So unit area capacitance is Cox, which is farad per meter square, standard units, or micrometer square in this case. Now how to get the total capacitance? If I know the unit area capacitance, can I get an answers in chat box? So see that your unit area capacitance is Cox, that is measured per unit area. So to get the total capacitance, this should be multiplied with area. Very good. Yes, it should be multiplied with that. What is the area? area of the channel. So how will I get area of the channel? Area of the channel can be obtained by multiplying the dimensions of the channel. You have width of the channel and you also have length of the channel. So I will write this as WL into Cox. I hope this is clear. I'll just put this as equation number 1. I'll definitely open for discussion. Let me just finish a bit more from this. Right. So this is the initial charges in the channel when a very small VDS is present, or when your VDS is almost negligible. In that case also, this is the channel charges. Right. Now I'll bring in the effect of VDS. Now, if I'm applying VDS, that will actually result in, or that will establish an electric field. So application of VDS will definitely establish an electric field where across the length, because VDS is applied between source and drain. So an electric field will be established between or across the length of the MOSFET, right? Now, how will I express that? I can express this electric field again. I'll write the magnitude as the voltage applied, which is VDS, divided by length of the device. So the electric field can be written as equal to VDS by L. I hope this is clear. Moving forward, now what I want here is I want to bring in this VDS, and I want to write the, finally what I want to write here is actually the current, right? So how will I write current? Say I want to know, I know the charges, I know, so why I'm writing current here? With the VGS voltage, I know what is the channel present and what are the charges in the channel. And now since we are applying VDS, definitely a current will flow. Now I am looking at what is that current. So I can write current ID. So probably you remember these relations. Q is equal to I into T. So I can definitely write I as Q by T, right? Now how to get this time factor in this case? So that is obtained again by under or writing the velocity of the charges which are moving, right? Since we have applied a voltage, that is establishing an electric field that will result in movement of charges. That means if when the charges starts moving, there will be velocity, right? So now I can write the velocity V as mu charges. How will I write? Yeah, so velocity of the charges is proportional to the applied electric field. Velocity is proportional to applied electric field, or I can write this as velocity of is equal to mobility into electric field. I hope this relation is known for you guys. Otherwise, you can take this now. Now, what is this electric field? This electric field is actually created. Electric field is actually created by a voltage. What is that voltage? VDS. So it is equal to mu n into VDS by L. I hope this is clear. All right. Now, so how will I write current? Current can be written as, so I know what is velocity. I want to write something in terms of time. So velocity and length is there. So I know how velocity and time are related. So with that, I'll just modify this. I will write this as Q by L into V. Right. I hope that is clear. Velocity is distance by time. I have used the same relation here. So your current ID is equal to Q by L into V. Or further, if I write that, I can write this as Q is WL into Cox into VGS minus VT. What is V? V is mu n into VDS divided by L. Or if I write this in a better form, it is mu n Cox W by L, mu n Cox W by L, VGS minus VT into VDS. All right. I hope this is clear. So if you have doubts in this, please unmute and you can ask, or you can put in the chat box. Till now, what we discussed. Is this clear?
So one down.
Yes.
Now we are applying VDS, right?
Yes.
So that voltage term, won't it be VGS minus VT minus VDS now?
Okay, where? Which term? Which term where?
So ID is equal to
Okay.
COX into
Mhm.
VGS minus VT minus VDS. Like channel will decrease. I mean that voltage it will decrease the.
Yeah, so I'm yet to consider that actually. I'm yet to consider that completely into this. So what I have written here is, see, you have a channel present. Now assume that you already have a channel. It is not by the application of VGS. In that case, I can actually write only in this form, right? I know this amount of charge is present, right? I know this amount of charge is present, and now when I start increasing this VDS, a current will flow. That is what I have taken here. I understood your point. Now your question is, why didn't you consider the voltage available in the channel?
Yes.
Right. Now, in fact, I have taken into consideration of the voltage in the channel itself, assuming that your VGS is equal to VGD, or this condition is what I'm assuming now. I'm applying a VDS, but that VDS is very small.
Okay.
All right.
Got it.
Now, the point you have taken now, second step of ID. I'll do that, Praveen. So what I'm telling is, I'll be considering the effect of VDS also now because I am doing in stage by stage so that you will understand better. All right. I'll show this pictorially, and after that, still if you have doubt, you should ask me at the end of the class. All right.
So this whole case is for small VDS value.
Yeah, I'm just writing for small videos. Yes. Please hold on, Karthik, and I didn't see the who has asked the same question. I'll be just showing you pictorially what I'm trying to write analytically. Just hold on. Yes, Karthik. Yeah. Thank you.
Okay, sir.
Okay. Praveen, the second step of ID again. Second step of ID, whether is this step or this step. You can unmute, Praveen.
Sir, last second, sir.
This one.
Yes, sir.
Okay, all right. So what I have done here is, I know the drain current I can write as Q by L into V. Now what is Q? Q is this factor, WL Cox into VGS minus VT. Now what is V? Velocity. Velocity is mu n into VDS by L. Is it clear?
Oh, yes, sir, got it.
Okay.
So,
Yes.
so in this step, the one you're showing right now, the denominator should be L square, right? Because there's
Oh yes. All right. Yes. Wait. I think I made a mistake here. Yeah. So what is yeah, the time factor should be L by V, right? 1 second. Just let me look into that. One second. Let me check where I made mistake. This is correct. Now moving on.
no, sir, from the first step when you've come to the second step, there was already a L in the denominator.
Yeah,
And
yeah, I got it. I am just looking where I have made that mistake. All right. Yeah, I think it is correct only because it is L by V, right? So that means charge is WL Cox by VGS minus VT. Then I'm actually L is there, and then I'm substituting V. Right. That is mu and VDS by L only. Correct. This L and L is cancelling, and still only one L is in the denominator. I think it is clear. Is that clear?
Yes,
yes,
sir.
sir.
All right. Okay. Yes. Uh, so this can also be written in this form. I will write ID as mu n Cox W by L into this is VOV. VOV is overdrive voltage. I hope I have mentioned that. Yeah, overdrive voltage we mark it as VOV, or sometimes we write this as VOD also. Right? Various notations are there. So VGS minus VT is in fact I have written it as VOV, and then it is VDS. Right. Now, so what I am assuming here, VDS is small. So for a small VDS, in fact I can so what is happening here, if I look at the current equation, as you vary VDS, you will actually get a variation in current, right? A linear variation, because the other things are not going to change. So you are actually getting a linear variation. That means we can understand that at this point channel behaves as a linear resistance. Channel behaves as a linear resistance, and who is controlling that resistance? That resistance is in fact controlled by another voltage. Let us see that what. So I hope this is clear. If I am varying VDS in small increments, I will also get an incremental change in ID. If I change VDS by a small quantity, ID also will vary. Since that variation is looking as linear through this relation, I have written here that channel behaves as a linear resistor. Now, if channel is a linear resistance, what is the resistance value? So I can write the resistance value by just writing what is VDS by ID. VDS by ID is 1 by mu n Cox W by L into VGS minus VT. This is actually the channel resistance, right? Now, if you look at the resistance value, this is resistance. Now, this resistance is a linear resistance, but it is controlled by this overdrive voltage, or this is controlled by VGS, the voltage which is applied at the gate. So, when your VDS is small, in fact, I can write channel is actually equivalent to a resistance. Now, there is a linear resistance, but it is actually a varying resistance also. I can consider this as a voltage variable. It is a variable resistance. It is clear, right? Because how I can say it is variable resistance? The resistance can be varied by varying the VGS voltage, right? Now, so we have written the resistance of the channel. In a similar way, I can also write the conductance of the channel. What will be the conductance of the channel? Conductance of channel will be inverse of this resistance. So conductance can be written as mu n Cox W by L into VGS minus VT. Right. I hope this is clear. Now, if I try to look at the Cara, if I try to plot the Cara, the same thing is clear. So this is VDS, this is ID. For small voltages of small values of VDS, you will get actually linear variation. Right. I hope this is clear. Hold on. Now we will just see pictorially. So we will look at the voltage what we are applying, and also we will look at the shape of the channel. Right. So what I will do here is say this is my VGS voltage. This is VGS voltage, and this much is VT. So I will. So this is my source end. So what I'm drawing is what I'm trying to draw here and showing you is actually the voltage which is available to the channel and shape of the channel. So this I am calling it as source end, and this is actually drain end. Now I have applied a VGS which is greater than VT. So the voltage available to the channel is this much. At source end I have VGS minus VT. At drain end also I have VGS minus VT. This is the voltage available. Now, if this is a voltage available, this will in turn create a channel, right? Now, again, if I look at the channel, I'll draw channel somewhere here. Yes. This is again source end, and this is drain end. If I look at the channel, channel will be uniform. There is a uniform channel because of the voltage, the same voltage available at both source end and drain end. So this is channel. Now I will write one more thing here. At this end of the channel, I have a voltage available which is proportional to VGS minus VT. Similarly, at the other end also I have a voltage which is proportional to VGS minus VT available. That is why I have a uniform channel. Right. Now, since at both ends you have VGS minus VT, if I look at the average voltage available across the channel, what is average voltage available? Average voltage will be VGS minus VT plus VGS minus VT by 2, which is equal to VGS minus VT only, or it is VOV, that is the average voltage. Now what I have written for the drain current equation? Drain current equation I have written as mu n C of W by L into VOV into VDS. This is what I have written the drain current equation. Right. I hope this is clear. So here the channel is formed. So this is the voltage actually available in the channel, VOV. The average voltage throughout the channel is nothing but VOV. And you have applied a VDS. For that VDS only you got a current. This is my case 1. Right. In this case, one more thing I can write here, VGS is equal to VGD. Right. Now we will look at second case where we want to see how the channel is getting modified. The channel shape is getting changed. So to understand that, I am considering it as case 2 where I am actually applying VDS. VDS is keep on increasing. So let me, I hope the first graph is clear. If you have doubts, please put in chat box. So let me finish this, because if you finish this in one stretch, you will get a full clarity on this. So this is voltage available, and this is actually the this is source and drain end. This is again source and drain end. What I'm drawing here is the voltage available in the channel and the channel shape. Now the other things remain same. This is your VGS. I'm not changing your VGS. So VGS is this much, and in that VT is this. So what is available in the channel is actually VGS minus VT. But what is happening here? I am providing VDS. Since I am providing VDS, what is happening? Previously I wrote VGS is equal to VGD. So in this case, I have to write both things. I will write here as this is VGS at source end. There is no other disturbance because there is no voltage, no other voltage coming at the source end. But at drain end I have VGD, and that VGD is now VGS minus VDS. This we have already mentioned. Now what is happening here? VDS is increasing, in turn VGD is actually reducing. Right. Now since your VGD is reducing, what is happening? The available voltage in the channel is in fact reducing. So how I should mark? At the source end, I have the voltage, the whatever voltage I had previously, the same voltage I have, which is equal to VGS minus VT. Source end I have, but at drain end, it is not like that. At drain end, what is happening? As VDS is increasing, your VDS is increasing, so the available voltage is actually reducing. So from source end to drain end, I have actually a drop in voltage. I will just mark in this way. From here to here, if I move, it is actually changing. So what is the voltage available in the channel? Only this much is available. What is the rest? I had VGS minus VT towards this side, but now I have this new voltage. VDS is coming into picture. Since VDS is increasing, the effective voltage initially was here, this much was there. Because of increase in VDS, the voltage is actually reducing, and whatever is available is only now this much. What is that voltage? Now I will write that term here. This is equal to VOV minus VDS. I hope the question, I hope, I think who asked that question? Karthikeya, right? Yeah, someone asked this question, why that voltage is not considered as VGS minus VT minus VDS. Yes, I am considering that now. Right. So one thing you should understand is, because of the application of VDS, your VGD is reducing. Now what I have marked using this yellow color. So at this end, at the source end, I'm showing here actually. So at the source end, I have this VGS minus VT available, but at the drain end, drain end, what I have at the drain end is only VOV minus VDS, because VDS is the extra voltage that has come in, right? So because of this, what will happen to my channel? Channel also will be proportional to this voltage. So at the source end, you have the complete channel present, but as we move towards the drain end, your channel is actually getting a tapered shape, and it is something like this at the drain end, right? So still I can write that here the voltage is proportional to VGS minus VT, but here the voltage is proportional to what? It is proportional to VGS minus VT minus VDS, right? The voltage is proportional to VGS minus VT minus VDS. Now let me look at the average voltage available still. What is average voltage? The average voltage is actually VGS minus VT plus VGS minus VT minus VDS divided by 2, or this can be written as VGS minus VT minus VDS by 2. This is the average voltage. Now I am plugging in this in the same previous equation. ID is equal to mu n Cox into W by L into. Now what is the average voltage or the voltage available in the channel? It is not VOV, it is actually VGS minus VT or VOV minus VDS by 2 into the applied voltage VDS. Are you getting? I hope this is clear now. Or let me write this further in this form. So, so I have written this current equation as this, or if I write this further, I can write it as ID equal to, what is this, mu n Cox W by L into VGS minus VT into VDS minus VDS square by 2, which is in fact we call this as the linear region equation, drain current equation. Please unmute or please clarify if you have doubts. Whether this graphical representation gave you a little more clarity or you are confused now. Can I get some response in the chat box?
If VDS is small, VGS minus VT is the voltage throughout the channel.
Yes.
And if it's if VDS is significantly big, then at the other end it's VGS minus VDS minus VT.
Yes, yes.
Okay.
Yeah. So what about others? I'm frequently getting responses from few guys, and I don't know what others are doing. Please, I just want to make everyone comfortable here. If you are not getting clarity, please don't be hesitant to ask, right? So usually in a physical class, in an offline class, does this mean that current throughout the channel is not the same? Okay, I'll answer that, Parnika. Yeah, I'm just telling to every one of you that you don't, what to say, don't be hesitant to ask doubts, because in a physical class I can say, okay, still people will have problem like asking in front of others, but now you have all freedom actually to put doubts in your chat box, right? Even in class also you have, but then there we have to wait for one to ask and other to ask. Now you can actually put all your doubts here, I can clarify one by one. Yes, now answering to Parnika, does this mean that the current throughout the channel is not the same? Now current, what, so we need to understand what is current here. So current is basically movement of charges, the flow of charges, right? Flow of charges, and that will happen when there is an electric field created or when there is a potential difference. Now, since potential difference is there, current will be actually flowing. Now, initially we can observe that current was proportional to the applied voltage. At the later side or on the later half, when the channel is getting tapered or when the channel is getting pinched off and when the channel is getting moved away from the drain end, then current, there is no option for current to increase further. Right. I'm talking about an ideal, very ideal case. There is no option to increase further, but the current will not cease to zero, or the current will not cease to exist. Rather, the voltage which we are increasing will is sustaining that current. So maybe to be very precise to your question, charges throughout the channel is different, but the flow of charges is maintained by using a voltage called VDS. So hence current will be there. Is that clear, Parnika? All right. Okay. So moving on. So we have considered the second case as VDS is increasing. Now, what is happening finally? Finally, this VDS is increasing, and see, now you can see that there is some voltage available in the channel, which is VOV minus VDS. But as you keep on increasing this VDS, even that is reducing to 0. So that can be considered like this. So again, this is source end and this is drain end. So this is the voltage VGS. Now that has to be more than VT. So to the channel, for the channel, to the source end, still I have this VGS minus VT. But your VGS is not equal to VGD. And what is happening to VGD? VGD is VGS minus VDS. And now this VDS is increasing like anything, right? That means your channel, initially it was tapering, and at this point it has actually pinched off, right? This happened. So what is the meaning of this? This will happen when now your VDS is equal to VGS minus VT, right? When your VDS is equal to VGS minus VT, the effective voltage, I hope this is clear for you guys. See, now your VGS is equal, your VDS is equal to VGS minus VT, right? Now, what will be your VGD? Your VGD is VGS minus VDS, right? Now, this is VGS and your VDS is VGS plus VT. So your VGD is just VT. That means you have a channel just present. That is the case, right? Now, if I draw the channel at the this end, so if I draw the channel, this is again my source end and this is my drain end, and the channel shape has come like this, where this is proportional to VGS minus VT, and here, so here in fact you can see that a 0 voltage is actually there, right? Because your VDS has increased to VGS minus VT, and this is your VGS minus VT. This whole thing is VGS minus VT. So in fact you have the voltage available in the channel is reduced to 0. So if I look at the average voltage, again if I look at the average voltage, is VGS minus VT plus 0 by 2, which is equal to VGS minus VT by 2. So when I plug in this in the other equation, ID is mu n Cox W by L into what is the voltage in the channel, which is VGS minus VT by 2. And what is VDS? VDS is also equal to VGS minus VT. That means this will give you the expression half mu n Cox W by L into VGS minus VT the whole square. Right. So at this point, we say that the MOSFET current will not increase further, and from here onwards, we will identify this as saturation region. Right. So with one more additional point, I'll be just winding up, and I can take questions now. So this is your VDS, this is ID. So initially it was increasing, and after one point it is actually reducing to 0. This is VGS minus VT. Right. Now this is what is happening, or this is what we generally call as an ideal MOSFET. You have a MOSFET and you are applying VGS and you are applying VDS here. So initially your current will be proportional, later current will be constant. So what is the meaning of this? So if I look at the output carrier, if I look at this, I can say that in your saturation region, even if you change VDS by a small quantity, what is the change in current? Change in current will remain as 0. Right, in saturation region, even if you provide a delta VDS, a small change in VDS, change in current is negligible, or it is equal to 0. So that will give you, or with this we can say that the resistance of the MOSFET, right, or from this cara I can say that in saturation region MOSFET is actually acting as a current source, or to be very precisely it is a constant current source. And what is the resistance of the current source? Resistance of the current source is infinity. We call this as out. We will revisit these things. We will call this as output resistance. I'll tell you the why that we call this output resistance. It is an incremental resistance. It is like when we give a small change in voltage, we are looking at a small change in current, but that change in current is in fact 0. So we call this as incremental output resistance, which is delta VDS by delta ID, and that is equal to 0. And this is true, all these are true in the case of an ideal MOSFET. So next class we'll see why I'm calling this as ideal and what are the non-idealities, right? So from whatever I have written now in green, from this onwards I'll be explaining again in the next class. So what we did today is we have looked at current voltage characteristics. We started with an assumption that, not an assumption, we started with the understanding that your MOSFET is having a uniform channel. With that uniform channel, we looked at the voltage available at the source and drain, and we obtained the average voltage. With that, we have written the current equation as per this equation. Then as we keep on increasing VDS, what is happening? Depending on that, how your channel charges will be altered and how the average voltage is getting modified, and we are arriving at the linear region current equation, and finally to the saturation region current equation. Right. So everything started from the basic device physics equations, how to write charge, how to write electric field, and how to write drift velocity. All right. So with this, I'll be winding up for today's class. Thank you so much for listening. Now I can take questions. Thank you.